So let's do this static problem. We have this tension force, this gravity, and the other tension force, and we want to figure out if we know the direction of V and H. So V is vertical. For static equilibrium, the vertical force must cancel, and we see the vertical component for all the other forces are all going downward. So it must go upward, so we for sure know that V must go upward. But the horizontal component for this load is pointing against this tension. So for H, it might go the other way, and we don't know yet. But we don't need to really know the direction, because for the wrong direction, we'll just get a negative. Negative. It's just going to be negative if we have the wrong direction. And that doesn't stop us from assuming H goes upward, because if we get a negative answer, then we just know, oh, it should point the other way, and that's it. Good. So now we should choose a pivot point. Let me choose this point. I'm choosing this point because then the torque caused by H and V are both zero because they act on the pivot point. If I choose any other point, I can only make one force to have the zero torque, but by choosing this point, I can get rid of H and V. So now I can figure out the torque caused by all other force. Let's arrange them with clockwise and counterclockwise. For clockwise, we have the weight and load. So we have the bar weight, let's say it's mg, and the load will be, let's say it is w. And for, so for the tension force, it's going to be counterclockwise, so it is the only counterclockwise force. Now we can extend all the force with dotted line. So let's extend this force. Here's tension. Here's the load. Let's extend all of them with dotted line. And we have gravity. We don't need to care about V and H because they are not going to generate torque anyway. Now we want to find the perpendicular direction of these forces to the pivot point, which is at here. Here's our pivot point. Let's start with this horizontal tension force, because here is the dotted line, so the closest distance will be this one. And for the loading, the closest distance will just be here along the rod. And for the weight here, the closest distance is going to be this one. So now we find all the three arms. These are called this force arm, moment arms. We have all the three moment arms, and we can use geometry to figure them out. We can say this is the, let's call this angle theta. We don't need theta at the end, but it is good to have some intermediate symbol to help us analyze the problem. And let's say the total length is L. Then here, this moment arm will be L sine theta. The load is tied at a 3/4 of the bar, so the moment arm of this load will be 3/4 L, and the moment arm of here will be half L times cosine, because it is acting on the center of the rod. So now we can multiply the force with the moment arm and set counterclockwise equals to clockwise. So for clockwise, we have mg and w. So let's say it is mg. Here's mg. It is 1/2 cosine theta plus the load is here, which is w times 3/4 L equals to the tension here times L sine theta. So here we have our torque balance equation. So do we care about the length of the bar? No, we don't, because you see the length can be factored out. So at the end of the day, we only care about the force and this angle, and the length will not affect the final result. So it's a no here. Alright.